Have you ever wondered that a tree and a capacitor are quite similar to each other when you're comparing tree to rain and a capacitor to electrical currents? Because when the rain starts, it does not actually start for this person, and when the rain stops, it also does not stop for this person because the tree needs to shed some of its stored up water in its leaves. A similar thing happens in this electrical circuit also. I should draw a switch in here somewhere. Um, and executioner who is flipping the switch. So this poor guy is getting electrocuted, but not as soon as this executioner flips the switch to on, because the capacitor needs charging, and only after the capacitor has charged, current starts flowing through this path. And also when the switch is opened, this person still experiences a current flowing through him if he is still alive, because this capacitor needs to get discharged. So yeah, this is not what the video is about. This is just an interesting comparison which came to my mind before shooting the video. Well, if there is if there has to be a topic of discussion in the comment section, this could be it, because the topic of this video, to be honest, is quite boring, mundane, and found in textbooks. So let's get on with the boring stuff. Yes, we are going to talk about oscilloscopes today. I'm going to go over the very basic building blocks and working principles of this instrument, and I'm going to try and give you a very practical overview of this instrument and how it works. And the main goal of this video is to develop a common sense among the viewers regarding the usage of this instrument. So before diving into the main building blocks, I would like to mention 2 points. The first one being that this is also an electronic or electrical instrument like any other, and this also has its own limitations and imprecisions when it comes to certain aspects. So we must keep the non-ideality of this instrument in our minds. Often we tend to forget that. Often we consider this instrument as a very ideal instrument and a very accurate representation of the signal which is fed, but that is often not the case. So we need to keep in mind certain very basic things, like this probe which we are using to measure electrical signals has a capacitance and a resistance. The capacitance is somewhere around 16 picofarads and might be some tens of picofarads in different other probes and input sections. And the input impedance of this oscilloscope is 1 megaohm, and it might also differ with different variants, but more or less it's a very high impedance in the range of megaohms and very high kiloohms. So the next point which I would like to mention is about the probes itself. So these probes are coaxial cables, and if you know what a coaxial cable's cross section looks like, you would know that that there's a center conductor and there is a outer covering of a metallic conductor. So if you're bending the cable at a very sharp angle, I mean even sharper than this one, the cable's internals would experience unwanted forces, and because of those forces it might break, it might get ruptured internally. And I have personally seen so many oscilloscope probes which are non-functional because they were stored in an improper fashion. They were bent, they were twisted, turned, and just handled in a very improper fashion. So you need to take care of the oscilloscope probes. These are quite delicate and they might break internally if you are not careful with them. All right, so now those 2 points are out of the way. I can get into the main building blocks of an oscilloscope. So the first one is a cathode ray tube, or CRT in short. Now you might wonder, why am I talking about a cathode ray tube when I have a digital oscilloscope in front of me? I'm talking about a cathode ray tube because when we have to explain the workings of an oscilloscope, we really have to dive down to the basics, and we need to call upon the grandfather of all oscilloscopes, which is the analog counterpart of this instrument, which is a CRO, or a cathode ray oscilloscope. In cathode ray oscilloscopes, cathode ray tubes were used to display the signal and also to form the signal using a electrostatic beam. So really this digital oscilloscope is excuse me, this digital oscilloscope is a very digitized simulation of what a cathode ray oscilloscope would do. So yes, of course, this operates in a digital domain. This has FPGAs, ADCs, DACs, and all those digital circuits, not analog ones, but still this is logically a simulation of what the analog counterpart would do with a certain signal. So to understand the logic, we need to take the help of cathode ray tubes and CROs. So the first one which I'll discuss is the cathode ray tube. The second one is called the vertical amplifier. Now we do not know what vertical and what horizontal is yet, so let's just call it the signal amplifier. Now you can understand that this component is used for amplifying or even attenuating the signal, or the actual signal which we are going to measure with the oscilloscope. The third point, it's actually quite hard to write with a camera in front, but anyway, the third point would be the time-based generator. We could also call this as a ramp generator. This circuit is used for generating a time, signal which is linearly varying with time, so that we can have a constant slope with the time axis of that signal, and we can in fact use that signal as a time signal, or we could use that signal as to signify the passage of time, or we could, in other words, use that signal in the horizontal axis. The last point which I'm going to mention is the trigger mechanism. And I'm not going to explain all these circuits in detail, but I'm going to explain what they do and what their purposes are, and just to give you a sense of how the entire block diagram, or how the entire chain of operation operates. I should not call it the chain of operation. It's actually just how the entire instrument operates. First, I'm going to draw a diagram of the cathode ray tube. It's going to be quite hard with this camera in front. Now this is a filament. This area is a filament, and this filament is responsible for generating the electrostatic beam, and this filament is powered by a high voltage source. After the filament, we have a focusing arrangement which focuses the beam into a fine electrostatic beam. After that, we have a pair of vertical deflection plates. Let's call it the VDPs, vertical deflection plates. And this is responsible for a vertical deflection of the beam. After that, we have a pair of horizontal deflection plates, which is, as the name suggests, is responsible for a horizontal deflection of the beam. And finally, we have a phosphor coated screen on which the electrostatic beam falls and creates an illumination at the point where it falls. There might be accelerating electrodes over here powered by high voltage sources, but those are not that important. So if we are looking at this arrangement from the front, the two pairs of horizontal and vertical deflection plates would look something like this. If we are viewing it from the front, there will be a pair of vertical and there will be a pair of horizontal deflection plates. These two are the vertical deflection plates and these two are the horizontal ones. And at the middle of these two, there passes an electrostatic beam, which is being deflected by all these four plates. And as you can understand that these two vertical deflection plates are responsible for a vertical deflection of this electrostatic beam, and similarly the horizontal ones are responsible for a horizontal deflection of the electrostatic beam. And as a result of these two deflections, an instantaneous deflection of the beam would be, say, a vector sum of the horizontal deflection or the instantaneous horizontal deflection and the instantaneous vertical deflection. Now I just covered the CRT part of the 4 points. I covered this one. Now I'm going to cover the vertical amplifier, time-based generator, and trigger mech. I'm going to cover these three in one go because all these three are part of the entire block diagram. So I'm going to draw the entire block diagram and I'm going to explain what those functions are. Now, say we are supplying a signal from this source. First we have a coupling arrangement, and then we have the vertical amplifier, which is the signal amplifier, and the output of the vertical amplifier goes to a delay line circuit. It is not that much important, so you can just ignore that. And there comes a signal from the vertical amplifier into the trigger mechanism. This trigger mechanism then feeds into the time-based generator. Time-based generator feeds into a horizontal amplifier. This is a vertical amplifier. Well, I have ordered slate pencils, but for the time being I'm using chalk, so the writing is horrible. Yes. The horizontal amplifier is then energizing the horizontal deflection plates, and similarly the vertical amplifier is energizing the vertical deflection plates. Alright, this is the entire block diagram. Stripped down to its very basic components inside an oscilloscope. And over here, mind you, there's a switch. You can switch between AC coupling and DC coupling. DC coupling is nothing but a straight conducting wire to the vertical amplifier, but in the case of an AC coupling, we have a DC block capacitor. So suppose the signal is like this. There's a sine wave with an average voltage of 5 volts. If we are coupling it if we are AC coupling it, then before the amplifier at this point, the signal would shift down on the 0 volt axis. This capacitor just blocks all the DC voltage component out of the signal. So yes, this is the entire block diagram, and let's start with the vertical amplifier. So when we are feeding the signal, we sometimes see that the signal is too weak, or let's just show you a practical example of that. Suppose when we are feeding the signal was like this. So we need to amplify the signal to make proper measurements. So we just adjust the gain of the vertical amplifier, and in that way we are amplifying the signal which is being displayed on the screen. And with this knob, what I'm doing is I am just adjusting the gain of this amplifier. Right, and from the vertical amplifier we are pulling a trigger input. And what I mean by that is, say let's just consider this signal. We have a square wave like this, and we have set a trigger at a rising edge. So whenever this line senses a rising edge, the trigger mechanism generates a pulse and feeds it to the time-based generator. Now comes the functioning of the time-based generator. The time-based generator generates a signal like this, a sawtooth signal or an inverted sawtooth signal, which is fed across the horizontal deflection plates. Now, whenever the trigger mech generates this pulse and feeds it to the time-based generator, the time-based generator initiates a sawtooth signal from the 0 point. From this point, it initiates from this, shoots up, and continues. Now that this is because the time base or the horizontal deflection should start from the middle when there is a trigger. So a rising pulse trigger, setting a rising pulse trigger means that in the middle of the screen, we are going to have a rising pulse. So for that to happen, we need to start, or the time-based generator needs to start its sweep from the 0 point. Now let me just show it to you on the screen of the oscilloscope. Can you see that clearly now? Hope so. All right, we're going into the trigger menu, and inside the trigger menu we have a selection of the source of the trigger. So right now it's in channel 1, that's why this wave is quite stable. If we change it to channel 2, this wave will be dancing all over the place because the trigger input is not being sampled from channel 1, rather it's being sampled from channel 2. But since the signal is at channel 1, we are going to change it back to channel 1, and over here in the slope we have set it to a rising pulse. Now if we zoom into the center of the screen, we can see that at the center there's a rising pulse, and that was what I was explaining with the time-based generators function. So the time-based generator is generating a sawtooth signal specifically because it is linearly dependent with time. So when the I should actually draw it larger. Say over here we have the two pairs of plates. Now there is a sawtooth signal applied across the horizontal deflection plates. So the signal is like this. So when this signal is being applied across this, the wave starts from, or rather the electrostatic beam starts from a left deflection and sweeps to a right deflection, because the electrostatic beam is negatively charged and initially this plate is positively charged. So it attracts and then slowly this becomes positively charged and this becomes negatively charged. So it repels and this one attracts. And in the screen, it looks something like this. On the screen, the beam moves from the left edge to the right edge. And now adding with that the vertical deflection, and we are, as we have seen, we are applying the signal, the actual signal across the vertical deflection plates. So if we hadn't applied the horizontal deflection plate signals, the signal on the screen would just oscillate at the center vertically. So suppose there's a sine wave, it would just oscillate like this. But adding with that the horizontal sweep, we would get a sine wave which is like this. All right. So it is already sweeping like this, and then we add a time axis so we can view the signal in time. Now we can change the frequency of the horizontal sweep or the sawtooth wave. We can have a very low frequency. If we have a very low frequency, the time span given by the entire horizontal axis will get larger, and we would see a larger part of the sine wave. And similarly, if we shorten the wavelength of the ramp wave, or if we increase the frequency of the ramp wave, we are in fact squeezing into a very short time period across the entire horizontal axis, and we would see a very short portion of the signal. And let me just explain that to you on the scope. By using this knob, I am changing the frequency of that ramp signal, and now I am going to decrease the frequency, and I'm going to view a large part of the signal in time. So there are a number of pulses over here, a large number of pulses. So that takes a lot of time to generate. And now I am going to increase the frequency or decrease the wavelength of the ramp generator, or the horizontal sweep is much faster right now, and we are seeing less number of pulses or a lesser portion of the entire signal. All right, so we have covered the basic working of the trigger mech, the time-based generator. The horizontal amplifier is not that important. It just ensures that the ramp wave over here is correctly positioned and correctly amplified. And in fact, we can change the position of the ramp wave to change the horizontal position of the entire signal. We can bring it back to origin by just clicking this button. In certain oscilloscopes, that's a feature, and in certain, that is not a feature. Also, in this vertical section, we can rotate the smaller knob to change the position of, vertically, we can change the position. All right, so that I think covers the very basic working principles of this instrument. So the time-based generator generates a signal which is linearly dependent with time, so we can consider that to be a certain span of time, which is applied across the horizontal deflection plates, and that is creating a sweep of the electrostatic beam, and coupled with the vertical deflection of the electrostatic beam, we are getting the signal in time domain. So this is an instantaneous vector sum of the vertical deflection and the horizontal deflection that we are seeing on the screen. And the trigger mech is just for synchronizing the actual signal and the ramp wave so that the signal does not shift laterally it stays in one position. Right, and that is the basic um, working principle of an oscilloscope. Also, there is the coupling. If we are interested in viewing the DC part of the wave, we can change the coupling. No, for all you OCD guys, the chalk did not fall. The chalk is right here. So if we are changing the coupling over here to DC, we see that the wave shifts up, because this wave is not a bipolar wave. This is a unipolar wave. This is an unipolar wave, or in other words, the 0 volt is at this level, not in the center of the wave. If 0 volt was at the center, it would, a DC coupling would have looked like an AC coupling also. In the AC coupling, we are just getting rid of the DC part of the entire wave, and we are shifting it down on the 0 volt level. So I guess that's it. That's the basic working principle of the scope. So I'll see you guys in the next video. Thank you for sticking around for so long. I know this is a long video, but there were things to say. I hope you got an understanding of how to operate the scope, and please kindly do not press this auto button to set the settings of the oscilloscope. This is just a horrible button to have. Most cathode ray oscilloscopes do not have this button, because it is so easy to make a proper display of the signal by using all these knobs, and it is very logical and intuitive with these knobs. Just look at it. When I press the auto button, what happens to the screen? So you have a certain setting set up in the oscilloscope. After pressing the auto button, firstly, it does not accurately give you the signal. It's too much spread out in the time domain. And secondly, it switches on the channel 2, which is over here just no signal. The channel 2 is not connected over here. It is just open, and this is just AC noise from ambient appliances. So you have to manually switch off channel 2 and then go to channel 1 and change the coupling if you want to AC. What just happened? It just messes up the entire thing. Change the time base to something. Right, it has also changed the trigger to channel 2 for no specific reason. So back to channel 1, time to normal. Let's go back to AC coupling. There we have a proper signal. Right. So I guess you won't have to use this auto button anymore in an oscilloscope. Please do not use that. Probably I'll make another video about the functions or the special functions inside an oscilloscope, like fast Fourier transforms, measurements, cursors, and other mathematical functions like that. So that's it from this one. Hope you have a nice day. See you in the next one. Goodbye.